The carburation system must first of all control the air-fuel ratio in response to throttle setting at all selected power outputs from slow running to full throttle and during acceleration and deceleration. The carburation system must also function at all altitudes and temperatures within its operating range. Finally, the carburation system must provide for ease of starting and generally incorporates a means of shutting off the fuel to stop the engine. The float chamber carburetor is the cheapest and simplest arrangement and is used on many light aircraft. However, it's very prone to carburetor icing and may be affected by flight maneuvers. A fuel injection system, which will be discussed in the next lesson, is a more sophisticated arrangement. It meters fuel more precisely, thus providing a more accurate fuel-air ratio. It's also less affected by flight maneuvers and is less prone to icing. Any of these systems may be fitted with a manual mixture control, by means of which the most economical cruising mixture may be obtained. However, in order to assist the pilot in selecting the best mixture, some aircraft are fitted with either fuel flow meters, fuel pressure gauges, or exhaust gas temperature gauges. The carburetor employs two basic principles, those of the U-tube and the venturi. If a tube is bent into the shape of a U and then filled with liquid, the level in either leg will be the same, provided that the pressure acting on the ends of the tube is the same. If a pressure difference is created across the U-tube, it will cause the liquid to flow. In practice, one leg of the U-tube is opened out to form a small tank, within which a constant level is maintained by a float and valve mechanism. This regulates the flow of fuel from a fuel pump or pumps, which deliver a supply from the main aircraft tanks. Bernoulli's theorem states that the total energy per unit mass along any one streamline in a moving fluid is constant. The fluid, which is air in our case, possesses energy because of its pressure, temperature, and velocity. Any change in one of these characteristics will bring about a change in one or both of the others, in order that the total energy of the fluid flow remains constant. As the air passes through the restriction of the venturi, its velocity increases, causing a drop in pressure and temperature. The pressure drop at the throat of the venturi is proportional to the mass airflow. It's this pressure drop which is used to make the fuel flow from the float chamber by placing one leg of the U-tube in the venturi. In a float chamber carburetor, such as that shown here, airflow to the engine is controlled by a throttle valve, and fuel flow is controlled by metering jets. Engine suction provides a flow of air from the intake through a venturi in the carburetor to the induction manifold. This air speeds up as it passes through the venturi, and a drop in pressure occurs at this point. It must be noted, however, that within the induction manifold, pressure rises as the throttle is opened. Fuel is contained in a float chamber, which is supplied by gravity or an electrical booster pump, or by an engine-driven fuel pump, and a constant level is maintained in the chamber by the float and needle valve. Where fuel pumps are used, a fuel pressure gauge is included in the system to provide an indication of pump operation. Either pressure from within the cowlings or air intake pressure acts on the fuel in the float chamber, which is connected to a fuel discharge tube located in the throat of the venturi. The difference in pressure between the float chamber and the throat of the venturi provides the force necessary to discharge fuel into the airstream. As airflow through the venturi increases, so the pressure drop increases, and a higher pressure differential acts on the fuel to increase its flow in proportion to the airflow. The size of the main jet in the discharge tube determines the quantity of fuel which is discharged at any particular pressure differential, and therefore controls the mixture strength. The simple carburetor illustrated here contains all the basic components necessary to provide a suitable air-fuel mixture over a limited operating range. The U-tube principle, one of the two principles upon which the operation of the carburetor is based, requires that the pressure in the air intake and the float chamber be equal. Admitting atmospheric pressure in the float chamber by means of a drilling in the float chamber cover plate is not a satisfactory method of ensuring equalized pressure across the carburetor, because due to maneuvers and the speed of the aircraft, the changes in pressure localized around the air intake would not be readily transmitted to the float chamber. Equalized pressure conditions can only be obtained by connecting the float chamber directly to the air intake by a duct, which is called the pressure balance duct, shown here. As engine speed, and thus the airflow through the venturi, both increase, the proportion of fuel to air rises as a result of the different flow characteristics of the two fluids. This causes the mixture to become richer. To overcome this effect, some carburetors are fitted with a diffuser well, such as is illustrated here. The fuel discharge tube from the main jet passes through the diffuser well. A number of small holes are drilled through the wall of the fuel discharge tube at different levels. As engine speed is progressively increased above idling, the fuel level in the diffuser well drops, and progressively uncovers more air holes, which allow more air into the discharge tube, and by reducing the pressure differential, prevents enrichment of the air-fuel mixture. The process of drawing both air and fuel through the discharge tube also has the effect of vaporizing the fuel more readily, particularly at low engine speeds. A suction applied to a tube immersed in a liquid is sufficient to raise a column of liquid to a certain height up the tube. Should a small hole be made in the tube, under the same conditions, bubbles of air will enter the tube, and the liquid will be drawn up the tube in smaller drops rather than a continuous stream. In other words, the liquid will be diffused or made to intermingle with the air. Air bleeds into the tube and reduces the forces acting on the fuel, reducing the flow of liquid through the tube. This animation illustrates the principle being used on a basic carburetor. At low engine speeds, the volume of air passing into the engine is so small that the depression in the choke tube is insufficient to draw fuel through the main jet. Above the throttle valve, however, there exists a considerable depression, and in some carburetors this is used to effect a second source of fuel supply for slow-running conditions. A slow-running fuel passage with its own jet leads from the float chamber to an outlet at the lip of the throttle valve, as is shown here. The strong depression at this point gives the necessary pressure difference to create a fuel flow. The size of the slow-running jet is such that it will provide the rich mixture which is required for slow-running conditions. An air bleed opening into the area below the throttle valve assists atomization. The purpose of the transverse passage drilled through the throttle valve is to evenly distribute the mixture over the area of the induction manifold. A small hole in the transverse passage, which communicates with the high-pressure side of the throttle valve, acts as an air bleed. It draws fuel through the transverse passage to mix with the air passing to the engine. As the throttle is opened, the depression at the lip of the throttle valve decreases, and the depression in the venturi increases, to the point where the main jet starts to deliver fuel, and the flow through the slow-running system diminishes. Carburetors must be carefully tuned in order to obtain a smooth, progressive changeover between the slow-running and the main system to prevent flat spots. A flat spot is a period of poor response to throttle opening caused by a temporary weak mixture. It normally makes itself felt as a hesitation during engine acceleration. An idle cut-off valve is usually incorporated in the slow-running passage, and is used when stopping the engine. When the cut-off is operated, the valve moves over to block the passage to the slow-running delivery. The mixture being delivered to the engine becomes progressively weaker until it will not support combustion and the engine stops. This prevents any possibility of the engine continuing to run erratically due to pre-ignition, and also prevents fuel condensing in the cylinders, which would tend to wash the oil from the cylinder walls, causing lack of lubrication when the engine is next started. The idle cutoff may be a separate control, or it may be incorporated in the mixture control lever, as is the case with the Seneca system illustrated here.